Okay, hello everyone. So I'm going to give you some hints on second assignments. This assignment has 6 questions. Seems to be long, and due is this Friday. Now, but actually, as you're going to see, its bark is a lot worse than its bite. Okay, so no worries. So let's take the first question. First question is here. First order system, and which has a magnitude ratio of 0.707 at this frequency, and once you determine its time constant is phase shift. Okay, now this will bring us to one of the handouts that I give it to you in the lecture, and this is also uploaded on WebCT, so you can take a look at that. This is called Lecture 10, Summary on Measurement System Response. Okay, so summary on measurement response. Basically, it contains the formulas or the results based on the first order system response and the second order system response. Specifically, they are step response and sinusoidal response. So this is basically the first order system formula sheet. Okay, I'm not quite sure yet if I'm gonna let you to bring this to the exam, but for the time being, I suggest you remember some of the basic concept, okay, and very simple equations and solutions. So, for example, this is a solution for step response of first order system, and this is a solution for sinusoidal response of this first order system. And we look at that the definition for magnitude ratio here, m of t. So magnitude ratio basically is for step response is this current value compared to the initial value and with the step change, right? And it's a time function. And the magnitude ratio for sinusoidal input is a frequency response. It's a frequency function, so which is a function of the input frequency. Okay, and it's defined as output amplitude at a steady state divided by the input amplitude. And this is your output amplitude at steady state, because this whole term in here will go to 0 as t go to infinite. So this is not a steady state value. So this is your steady state value. And your input amplitude, right, is a k multiplied by a, so that's amplitude. Your output amplitude at steady state is ka over this quantity. So this ratio turned out to be just 1 over this one here, and tau is the time for constant. So that's why the magnitude ratio is a frequency function of the input frequency function. And the other quantity is called aerodynamics, and defined as gamma of omega equal to 1 minus m of omega. So if you know this, you'll know this automatically. Okay. Yeah. So for this particular question number 1, as you can see that it gives you a frequency, give you a magnitude ratio. So apparently we're looking at the sinusoidal response for a first order system, right? So how am I going to determine its time constant and its phase shift? So here's what you need to do. Basically, this is all of the equation in here. You need to either remember, or if I give you a formula, so that's how you need to be able to look up to it. Okay, look it up to it. So here's a magnitude ratio. Here is the phase angle. Here, the phi here is this one here, right? Okay. So let's go back to here and use this one here. Okay. So that's problem number 1. As we said, your m of omega equal to this quantity, okay? And right now what you're given, right, is f equal to 200 hertz. Okay, so be careful, you're not being given the omega, right? What you give is f. And what is omega? Omega equal to 2 pi f. So this is your input frequency, right? This is in terms of units reading per second. Okay, so you can calculate that easily. Okay, so that's your omega. Okay, and what do we know? We know that at 2 pi f, right? 2 pi f, this quantity equal to 0.707. So that equal to this. What's omega? Omega 2 pi f. Tau. Okay, so you know this, you know f, you solve for the tau, right? Solve for tau. Okay, so that's the first part. And the phase lag is phi equal to -10 tau omega. Once you solve tau omega, you can solve the phi. So that's very technical how to solve that. However, I do want to remind you here is in the class, the value of this value here, right? In the class, I did mention a very special frequency, input frequency. So when omega equal to tau, 1 over tau, okay, when omega equal to 1 over tau. So when your input frequency is the inverse of the time constant of your first order system. So what is, right, the corresponding magnitude ratio? So if you substitute omega equal to 1 over tau here, right, your magnitude ratio basically equal to this. And if you take 20 log of this quantity, it's equal to negative 3 dB. So we said in the class that this is a special frequency. We call that cutoff frequency. Or it also represents is the bandwidth, right? The bandwidth of this first order system. The reason is because for any frequency that is higher than this, your magnitude ratio will be too small. Okay, and basically your output magnitude amplitude, right, compared to your input amplitude is insignificant, and you can simply discard this system, or you can treat the system not giving any meaningful or useful information, right? So that's what the bandwidth is. So, and this is actually you can see the drawing, right, from the second question, right? So that's why we call what's low pass filter, right? You're only letting this is negative 3 dB. So you're only letting frequency within this range to go over the first system. Okay, higher than this omega b, and you don't think that's useful information because there's too much attenuation, right, after this bandwidth at here. Okay, so that's the first question here. The second and third question are two Excel exercise. Okay, so the second question, is, suppose you have a first order system with a time constant 10 milliseconds, and I want you to use the provided Excel template to generate a plot of f omega and phi omega plots. So I need you to generate 3 different plots. One is the plane m of omega versus omega. The second one is 20 log f omega versus omega. The last one is phi omega versus omega. Okay, and based on the plots, and I want you to calculate, right, based on the data, what is at which frequency the magnitude ratio drops to this negative 3 dB or 0.707, and what is the phase delay, okay, at that frequency, right? And the last question is, would you use this measurement system to measure a signal with frequency of omega equal to this? Explain why, right? So based on the templates here, okay, this is what I expected you to have, right? I think I provided you this, right? And I believe you also have this one here. So I need you to calculate this 20 here. You need to calculate the phi, okay, with the formula sheet. Okay. And then you produce the plot f of m of omega versus omega, 20 log m of omega versus omega. So these two plots are here, okay, and also the plot of phi of omega versus omega. Okay. Now one thing that you need to be careful is the x-axis. Okay, basically the omega axis needs to be in log scale. Okay. So double click on this. Double click on or right click here, format axis. Okay. Make sure that here the logarithm scale is chosen, okay, for this particular axis. Okay. Otherwise you won't be able to see the plots clearly because they're going to be all crammed together in a small space. Okay, so that's what you do. Okay, don't take a log of this, just logarithm scale. I think you can also do that inside, for example, layout. Okay, you can also do that in layout axis and primary horizontal axis and more of this axis. So you can also do that to pick this one here. Okay, yeah, that's how you use Excel. All right, so that's the second question. Okay, and but let's go back to this question here. Calculate what a frequency you have this much, and would you use this, right? So let's see here, right? Where is 0.7? So this is 0.707. Okay, this is 0.707, and at which frequency it's about 100, right? It's about 100 reading per second. Okay, that's about right, because we know that when omega equal to 1 over tau, right? And that'll give us the cutoff frequency, right? Yeah. Then the last question here, okay, would you use this measurement system to measure signal with a frequency of 300 reading per second? So let's take a look, right? Where's 300? 300 is over here, right? And the magnitude ratio at 300 is 0.316. So which means only 30%, right, of this output, right? The output amplitude is only 30% of the input amplitude, and that's way outside the boundary of this cutoff frequency here, which is 0.707. So this is why we say we are not going to use this measurement system, because the output of measurement system is not giving meaningful or useful information, too much attenuations, right? The other observation you can see is the maximum phase lag, okay, for a first order system is negative 90 degree. Okay, so that's you can clearly see that on your plot at here, right? Yeah, you start with 0 to negative. So it's very simple. Third question is, I give you those data here, and I also give you Excel file, okay, with the data in it. And we assume those data are obtained from a first order system is a temperature, and we want to know what's the time constant for this first order system. Okay, this question is essentially based on page 11 or lecture 8 notes. Okay, what we do is we want to plot a curve between log gamma t and t, so we can estimate time constant, right? So if I go back to my Excel file here, so this is the third question. You have this much here, and you have the temperature, and you need to calculate this column here, and also this column. Then you plot this column versus the time, and you'll get this guy here, right? Now, why? Okay, this column here is log of this column here, right? So this question is basically based on one of the lecture notes there. Okay? So as we said, this is a first order system. Okay, so the first order system of this question. Okay, that's the first order system for this question. And the solution for the first order system, right, as we know, or you look at your formula sheet, it's equal to T infinite plus T0 minus T infinite E negative 1 over tau T. Okay. So basically the so-called dynamic error, look at this one here, for first order dynamic error here, the error fraction of dynamic error is given by this quantity, which equal to that, right? Okay, so the gamma t, which is the error dynamics, okay, and that equal to this guy here. Okay, that equal to this, and which equal to g 1 over tau t, okay, aerodynamics. And if I take log of this quantity, so this gamma t is basically this column here, okay, this column. Okay. If I take log of this, as you can see that the other side, right, becomes this. So the plot between this and the t is the straight line, and the slope, right, is equal to negative 1 over tau. So if I can get a plot between log gamma t and a t, and my tau will be simply equal to -1 over that m, the slope here, right? Okay, so here is what we get here. You do the plots and you do a curve fitting. Okay, add the trend line, you do curve fitting, you get the slope, which equal to this guy at here. Okay, so that's this question right here. Let's take a look at the fourth question. Okay, this one is a little bit long question. You have a thermocouple and mirroring temperature fluctuation. We know it's a first order system. Okay. So the static sensitivity key is given. I want you to write down a differential equation for this measurement system. And a step input calibration system revealed that its rise time is this much. Determine the measurement system time constant. So what you need to understand, what's a rise time. So if I go back to here, what's a rise? Rise time means it's the output, right? When it reaches the time when output reaches 90% of this steady state value Ka. So he asks is what's the time constant based on this quantity, 4.6 seconds. And then given a fluctuated temperature of the environment temperature, I want you to determine the output. Okay, yeah. So in this part here, I'm going to say is basically, I'm not going to ask you to solve this, right? But you're solving it, but you're solving it based on the table here. So we look at this input as two portions here. Using superposition rule, we'll be able to get output E naught. Okay? And then we'll determine the time lag at this much frequency. Okay. So let's take a look at this question here. Okay, let's go over this question. Okay. So the first question is write down the general differential equation, right? And that's very simple. General differential equation. What's the output is this. And that equal to the key static sensitivity multiplied by your input temperature T, right? And the key equal to 2, so that's just equal to this. And tau value, we're not too sure yet. Okay, it's not given. So anyway, so we'll just keep it as it is, right? Okay. So the second question here, okay. Second question, let's assume 0 initial condition. If I assume 0 initial condition here, what the question says, basically, we know the time when it reaches 90% of its final value. So what's the final value? Maybe we should also assume a final value, right? We should assume basically input is a unit step input. So we assume this guy equal to, let's say, maybe a constant temperature. Okay, then we know that, right, based on this assumption, initial condition and a unit step input, we know that our output, right, if you look at the summary here, we know that our output, basically this guy is 0, okay, so output will be simply, right, substitute the value, you'll get that, okay, so the output will be equal to 2Tc, okay, and 1 minus E tau T, so that's the output here. Now, what's given is, at the t equal to 4.6 seconds, the output reach 90% of the step change, right? Step change. Okay. So at t, this E naught, right, 4.6, okay, equal to 90% of the step change. What's the step change? Step change means is the value between the steady, right, the state value minus, right, the initial value. Okay, so we know initial value is 0 because initial condition is 0. And what's the steady state value? Steady state value is not Tc because you're looking at the measurement system. So your steady state value is this it's a static sensitivity multiplied by Tc, so it's actually 2Tc, right? So you know this. So at this 4.6, that equal to this. So now you can substitute this guy, right, back over here. So 90% 2Tc equal to this whole bunch over there, 4.6 seconds. There. So you know this, and you cancel that. You can solve for the tau, right? For the tau there. Okay. So as a matter of fact, you can also see that, you see, I have a summary here. When t equal to that, right, your output reach 90% of this. Okay, so you can solve the tau like, but that's how you end. But that's how you get the idea, the formula over there, right? The third part is when the input t equal to 250 plus 25 sine 4t. Okay, and what will be the E naught, the output? Okay, so the equation wise, right, it's the same equation, but it just replace this capital T small t, the temperature, with this quantity. Okay, now I said I don't need you to solve, so what happens is, because we know the input, right, that equal to, so this is 2 here, that equal to 100 plus 50 sine 4t. Okay. So basically tau dE naught over dt plus E naught equal to t 100 plus 50 sine 4t. Tau, you get the value tau from here. What's the solution? So we need a solution based on this, a solution based on this, and that's a step input, and that's a sinusoidal input. Okay. So if the solution, so this is y1, y2, or in this case it's actually e1, e2, right? So in this case it's e naught 1 and e naught 2, and we just add these two together, right? So from a table here, I can get my E naught 1 from this equation. I can get my E naught 2 from this equation at here, right? E naught 2 from this equation. Okay. So overall, right, you will be able to get a solution for everything, right? For everything. Okay. Yeah. So let's see, right? So what do we get here? What do we get here? Okay. So what I'm gonna get here is, right, because now you do have this C here, but we don't know what this Y naught is, right? Y naught is initial depends on initial condition, basically. Okay, but if you look at my lecture notes, okay, look at lecture notes here. Okay, for 100 step input, okay, the general output, right? The general output for this one here is y1. Oh no, y1 e naught 1. Let's see, equal to c e negative tau t plus 100. Okay, yeah. So that's the c value depends on the initial condition here. That c value depends on the initial condition. Okay, but we'll solve the c value initial condition based on what the actual initial condition here is. And for the sinusoidal, right, input, our E naught 2 corresponding output, okay, corresponding output is similar. It's also CE of this T plus, okay, D value, basically that's 50 over this guy here, the square root here. 1 plus omega squared tau square, okay, and then okay, sine omega tau omega t minus tau omega cosine omega t. Okay, yeah. So a little bit different from the the formula sheet here is. This is based on the initial condition here. So so basically this is your C value here, right? And that's your C value at here, okay, for this one here, based on initial condition. But in this case, I need to solve this initial condition at the same time. Okay? So here's my general solution for E01 and E02 based on these two. Then overall, right, this plus that. Now these two constants, right, altogether you can combine into one constant. Okay, and that will depends on your initial condition here. Okay. Okay, there. So that's the overall output E0. Okay, and you know omega, you know tau, right? And you can substitute, okay, and you can get what you want. Now, what will be the value of C, right? What will be the value of C? The value of the C depends on initial condition, as we said, right? So what will be the initial condition then, right? The initial condition means what's the E0 value at t equal to 0, right? Now, the E0 value at t equal to 0, right? That basically equal to 2t, okay, of 0, okay, 2t of 0. So there we go. Where's 2t? There we go. It's this guy here, right? So when you substitute t equal to 0 here, that's basically 100. So that's your initial value, 100, right? Okay. So substitute this initial condition here. You can solve for the C value. Okay, the C equal to 6.16. Okay, 6.16. So once you get a solution there, and then you can solve for the last part, which is the phi value, right? At omega equal to 0.2 reading per second. You know the formula. Okay, you know omega, you know tau, and you can solve for the phi. Okay, this results coming here as a reading. Okay, and if the question asks you what's the time lag in terms of the seconds, right? In seconds, what you do is just simply phi over omega. Okay, the corresponding omega here, you get this one in seconds. Okay, so that's how you get. Okay, so this big question, okay, and right, so let's see the last question, which is not the last question. Yeah, problem 5. So problem 5 is about the second order system. Okay, it wants you to determine by calculation the damping ratio value of a second order system that will be required to achieve a magnitude ratio of unity when the sinusoidal input forcing frequency equals the natural frequency of the system. And then what is the corresponding phase delay? And in short, try to find the damping ratio zeta when f omega equal to 1 and omega equal to omega n, right? That's what it means here, basically. So to achieve a magnitude ratio unity, this is magnitude ratio equal to unity, when the input frequency omega, when your input frequency equal to the natural frequency of omega n, right? And what's the zeta value? Okay. In this question, you probably want to look at this formula sheet again. And the sinusoidal response for second order system is given over here. The corresponding phi angle and the corresponding magnitude ratio is given here. So this is your magnitude ratio. So we're looking for a zeta value so that this guy is 0 when omega equal to omega n, right? Okay. So let's take a look at this one. So m of omega equal to 1 over this portion, 1 minus omega n square plus 2 zeta omega over omega n squared. Okay. Now, so what's zeta when omega equal to omega n and such that m of omega n equal to n? If I substitute omega equal to omega n over here, right, and that means m of omega n equal to 1 over what? This term is gone, and that term is, right, square root 2 zeta and squared, right? 2z squared, okay, or equal to 1 over 2z. Okay, and we want this guy to be 1, so z equal to 0.5. There we go, right? Okay. So the last question is the phase at this particular condition. And if I look at the formula, phase is over here. Okay, so you can choose this one or this one to calculate the phi. Okay, give me 1 second. So okay, can you give me 1 second there? So this phi, right? Let's use this formula here for the phi. Okay, and use the phi here, right? Okay, equal to negative whatever angle there. Right. Sub zeta, sub omega equal to omega in here, and you get negative 90 degree. Now, a little bit difference here is my formula here is negative phi, so I put a phi here. There's no negative sign here, okay? But so when you put it here, you do have a negative phase delay here, right? Okay, but when I calculate this, I have an extra negative. Just tell you you have a negative 90 degrees phase delay. Okay. Last question. This is a strain gauge question we just finished on yesterday's lecture. Okay. Basically, you have a Wheatstone bridge over here, and what you are doing is you are having two identical strain gauge, which means the gauge factor is same, and mounted to sense axial strains. Okay, when you apply a tensile force. Okay, tensile force. Okay, axial force. Initially, the gauge is 120 ohms, and they're installed on the R1, R4 arm. The material of the bar has a Young's module of this much. Okay. Input frequency is 4 volts. The bridge output is 120 microvolts. Estimate the strain in the member, and what's the resistance change experienced by each gauge. Right, so that's the question. This question here, okay, really what I wanted you to look at, one of the examples in the lecture is for what's the results, right, based on that four-arm bridge circuit or four-bridge circuit. Okay, the results is delta E naught over EI. That's the same results based on the same circuits, right? So equal to GF over 4. Okay, assume you have four gauge sensors having the same gauge factors. Okay, so that's based on the 4 bridge. But for this question here, what we have is not a 4 bridge. It's actually a quarter. It's a half bridge, right? So 1 R1 and 1 R4. So now, as you can see, then it basically you're not going to have this term. You're not going to have this term. So you're going to have E1, E4 here. So the question is, what will be the epsilon 1? Will be epsilon 4? And because you're using two identical strain gauge sensor, and they are mounted at the same location. Okay, one at the top, basically the other one will be at the bottom. Okay, and you have a tensile force like that. So both strain gauge sensor will sense a tensile strain, okay, positive strain basically, and the amount of strain will be the same. So this equation here just becomes like that. Okay, yeah. Now this question will become pretty clear. Okay, and then based on this equation here, you can solve for epsilon, right? For epsilon, because you know EI, and you are given the delta change of the output voltage. You can solve for epsilon. And once you get the epsilon, you can use this definition for the gauge factor, okay, which is this one here, right? Because you know epsilon gauge factor, you know the R 120 ohm, so you can solve for the delta R. Okay, so that's basically this question. It's pretty actually straightforward. Okay, yeah. So it's understanding of how would you make use of this general equation in here. Okay. All right, so that's all the question. If you got any more problem questions, let me know. Okay, I'll be happy to help out. Thank you.